So, if we have two compatible observables, then we can find an eigenfunction f that satisfies both. I.e., we can essentially find a reality where we can nail down the values of both A and B to 100% precision without any uncertainty. We can find a reality where the two values being where the two values taking on some quantity do not contradict one another. So we can find f such that both a hat f is equal to lambda 1 or lambda a f, and b hat f is equal to lambda b f, where lambda a is essentially the actual possible values of A, and with the actual possible values of B. So there we go. We now know a zero commutator. So can we tell which three of these are compatible with one another? Now notice that these three are the same up to cyclic permutation. That is, I can switch Lx to Ly by just renaming this to x, renaming this to z, renaming this to z, and renaming this to x. So if you put every cyclic permutation means you switch every x to a y, every y to a z, and every z to an x. And through that, you can cycle through Lx, Ly, and Lz just fine. Which means that through cyclic permutation, we will be able to figure out all 6 possible commutators just by looking at the one, Lx, Ly. So let's do that. What is this commutator? Well, on the surface, it's just Lx, Ly minus Ly, Lx. So instead, we need to apply it to a test function. Lx hat, Ly hat, f, which is equal to 1. Lx hat, Ly hat, f, minus Ly hat, Lx hat, f. Now, we're going to have to expand that even more. So, we already know that Lx and Ly come with that scalar multiplier of I its bar. So since it's being applied twice here and here, we're feeling free to factor out that I its bar squared. What's left is a monstrosity. We get z partial y x partial z f minus z partial x f minus y partial z of the same exact thing. Then we have plus or minus x partial z of z partial yf minus y partial zf plus z partial x of z partial yf y partial zf. So here it is, beautiful monstrosity. And so, what happens when we distribute out these derivatives? And what's left is, we just have to use the product rule here. The product rule doesn't apply, well, it doesn't apply everywhere. But partial y of x is 0, which is you only have to consider when you take the derivative of this term. And I'll use that trick pretty much everywhere. So we get partial y partial z of f minus, that is not a y, so you'll hear about it, partial y partial x. Then we have minus y, we distribute this, get x partial z squared f. Whoops, that's a z, so we have to actually pay attention to what partial z does. But in this case, the derivative of z with respect to z is just 1, so we write minus partial xf, and then we write the
Isaac, 1 second. It's working. 1 second. Yeah. Nothing. Let me see. Where's the mic? This is the mic, I believe. Mic check. 1 2 3 4 5 6. Mic check. Mic check. 1 2 3 4 5 6. Mic check.
So we distribute this, then we get minus x. We distribute these terms, so it goes to z again, so we have to worry about it. We just get partial y f plus z partial y f. Also notice for any continuous functions, actually any continuously differentiable functions, you can actually commute the derivative. So partial z partial y f is the exact same as partial y partial z. So for our purposes, we're going to assume f is one of those C1 functions. So we can distribute that, and then minus y partial z squared f plus v, we have to distribute this. Oh, there's no x's here, so we don't have to worry about that. Then z partial x partial y f minus y partial x partial z. Now we're able to get down to some nice cancellation. Okay. So we distribute this. Over here we have partial y partial z. Now there's zx coefficient in front of it here, and if we look for it later on, we can see there's a minus xz coefficient in front of it there. Which means the whole thing has to go to 0. Then, if you look here, there's a minus z squared coefficient. So let's add our y plus xf. There's a minus z squared coefficient here, and if we look for it later on, wait for it, partial x partial yf, and times z is positive. So this also goes to 0. Then we have partial v squared f. The coefficient in front of it is minus yx. Wait a little bit. The other coefficient in front of it is minus x times minus y is positive xy. So this also goes to 0. Then we get a partial xf, but if you look everywhere else, it looks like there's not another. It looks like there's not another partial xf. Which means that this is probably standing by itself. We'll leave it be as plus y partial xf. Then we keep going. There's a partial yf, and it's also standing by itself. So we'll leave it. Over there, you see the partial z partial yf. But we already covered our basis for that. You will also see the partial z squared f, but we already worked with that. Here you will see the partial x partial yf. The only thing left is the partial x partial zf, which I skipped over. So you get plus partial x partial zf multiplied by, as you can see here, there's a minus zy coefficient. But earlier, there was a minus y times minus z is plus yz coefficient. This is also 0. So, of course, condensing everything down gives us minus h bar squared multiplied by y partial x minus x bar squared. We exclude the f. That means the commutator of Lx and Ly y h bar squared multiplied by y partial x minus x partial y. And that hopefully looks a little bit familiar, because if you recall, the LZ operator was just I bar y partial x minus x partial y, which means factoring out the I bar, rewriting it as I bar times I bar, this is just LZ, which means you get I bar LZ. There we go. So, you know that Lx and Ly give us I bar LZ, and by cyclic permutation, that means Ly and LZ give us I bar Lx, and LZ Lx give us I bar Ly. And for the other three operators, they're simply the reversed versions of these. If the commutator of A and B is negative, then the commutator of A. So here we go. These are the commutators. One crucial thing you'll note, unless one of the components is 0, which would by extension make one of the component operators is 0, which would by extension make that component of the angular momentum 0, none of the three are compatible. Which is very sad. When we plug things in to the uncertainty principle, we get that the standard deviation of our measurements with Lx multiplied by the standard deviation of our measurements with Ly will always be greater than or equal to h bar over 2. Remember, it was right there. It's 1 over 2y, the commutator of A and B. And of course, the commutator of A and B were I bar LZ. So we get something like this, which is unfortunately very, very sad. So we can't do anything about that. Can we find two quantities that are compatible? Well, the next optimal guess is to find the magnitude of L, or the norm. But you quickly realize that, what is this going to give you? The square root of Lx squared plus Ly squared plus Lz squared, which would be fine if they're scalars, but they are operators. Now, we've spent hundreds of years trying to figure out what this thing means to know results. So imagine what would happen, well, not to know results. There are a lot of results in fractional calculus. But imagine what would happen if we tried to mush multiple of them along with some non-operator coefficients under a square root. All hell will break loose. So instead of doing that, our next best idea is to try L squared. At least that doesn't give us a nasty square root, and the square terms are easy to define. They're just what happens when you apply an operator twice. So, is the norm squared of L compatible with any one of the components? Well, we have to test it. So, let's test it with Lx, and then we can use cyclic permutation once again in order to get Ly and Lz. So the commutator of L squared with Lx is 1. Since L is a linear operator, like every single operator we're going to see, this gives us Lx squared Lx plus Ly squared Lx plus Lz squared Lx. Notice how I'm not drawing the hats, because that would be one too many hats. We get Lx then what do we do about these other two? Let's first write out what these mean. Consider that the commutator of a squared and b is equal to a squared b minus b squared a. Oh, sorry, minus b squared a, ba squared. Now, it's tempting at first, even though you know it's not going to work, to rewrite this as maybe a times ab minus ba plus something. And then it hits you, this is just going to be a squared minus aba. So that's not going to work. Try to multiply a from the other side. Well, we get ab minus ba times a, which is aba minus ba squared. So that's not going to, hey, wait a minute. The problematic term on both sides is aba. So if we just add these two together because they have opposite sign for the aba, we should just get what we want. A squared b minus ba squared. Which means indeed a times the commutator of a and b plus, not minus, the commutator of a and b times a, which means it's different from just writing the commutator of a and b. This is what the commutator of a squared and b is. So now we apply what we learned to this. And we get Ly, Lx plus Ly, Lx, Ly plus Lz, Lx minus Lz, Lx, Lz. Now, notice the commutator of Lx and Ly is I e bar Lz, which means that the commutator of Ly and Lx is just going to be that but negated. We get L